Let's start our today's seminar, and we're happy to have Adeel Khan, who will speak on cohomology and intersection theory on stacks. Adeel, please.
Yeah, thank you very much for the invitation. So this is the kind of contents of my talk. First, I will explain some things about cohomology of stacks, and yeah, then I will talk about some intersection theory in this context. Then there will be kind of two parts at the end. One, it will be about localization theorems for stacks. And here I mean localization in the sense of kind of Atiyah-Bott type of localization, when we try to reduce something from some cohomology of the ambient space to cohomology of some subset. And then finally, I'll talk about some categorification of this story. So this part is kind of work in progress. Okay, so yeah, so for me, cohomology, I like to think about cohomology in terms of the six-functor formalism. So anytime we have a sheaf theory, so just kind of anything which behaves like constructible sheaves, so we have a six-functor formalism. So for example, we can look at topological spaces, at least, you know, maybe locally compact Hausdorff spaces. And then we can look at Betti sheaves. By Betti, I mean just sheaves. Betti is kind of to differentiate from étale. And then, yeah, for complex analytic spaces, again, we take the usual topology and look at sheaves there. We can also look at rigid analytic spaces, and then there's a formalism of étale cohomology and étale sheaves in the setting. And then, of course, in algebraic geometry, we have also étale sheaves with a six-functor formalism. So anytime we have something like this, we can take the following definition of cohomology as well as Borel-Moore homology. So we take derived global sections of the constant sheaf on X, or we take the dualizing complex. So this can also be written as omega X sometimes, where F is the map from X to the point. And so this is dualizing complex. If we take cohomology of this guy, we get the Borel-Moore homology up to sign, because it's a kind of homology, so it should be opposite grading. And if we just take cohomology of constant sheaf, so lambda here is just any commutative ring. And then, so yeah, in some cases, this can be a definition of cohomology, like in étale cohomology. In some cases, these things are already defined if we take singular cohomology or singular Borel-Moore chains. And then this is a kind of theorem of Grothendieck that these, you know, these constructions compute the same thing.
So if you work with, I don't know, say X is just a scheme, and you work with Zariski topology, so what happened?
You mean just sheaves with respect to the Zariski topology?
Yeah, kind of, obviously wrong choice, but
yeah, I think there's no good formalism of these Schrieg functors in this setting. We could take this definition. So this will compute some Zariski cohomology, but yeah, it's not so interesting, and I'm not sure if there's any notion of Zariski Borel-Moore homology, because I'm not sure if we have kind of Verdier duality and such theorems just for Zariski sheaves.
Yeah, I think it is. I mean, I think that, yeah, I think it is. You can work with Borel-Moore homology, which are dual to compactly supported cohomology, but of course not in a smaller generality. Yeah, okay.
Oh yeah, you mean you can just define it to be the dual, yeah. So if you have, because we can make sense of Zariski cohomology and compactly supported, Zariski cohomology, so we can just define the dual. Yeah, this could be a definition of Borel homology, but at least the theorems, which I will talk about in this talk, I don't know if it will apply in this way or not.
And I think if upper Ewing can also just defined using the sheaves with proper supports. So in case of you do with the schemes under Zariski topology.
I see. Yeah, it's possible. It's possible, yeah. But I mean, at the end of the day, the Zariski cohomology is not as interesting as Étale cohomology, at least from my perspective. I don't know. Yeah, so here I'd want to just take now the chain complex itself as an object of the derived category and say that somehow this is more fundamental object. So we can take this complex of singular cochains or Étale cochains and so on, or we can take these kind of Borel-Moore chains defined to be this way. And yeah, so just from the six-functor formalism, you have these kind of statements. So this is one example of a statement that you have here, which is just that there's an exact triangle or distinguished triangle in the derived category. Whenever you have a decomposition of X into a closed and open subsets. So this gives you the usual long exact sequence, but somehow it's nice to formulate it this compact way as a cofiber sequence or exact triangle in the derived category. And one thing which is really nice about working with this thing is that you can make sense of descent kind of results in a very naive way. Like, for example, if we take Borel-Moore chain complex, similarly, this would work with the cochains, but if we want to glue a Borel-Moore chain on X and we have two opens, then it's enough to specify some Borel-Moore chains on each open, and also to specify some isomorphism on the restriction. So this here means a homotopy pullback. There's one, this is something which has to be kept in mind, is that this is in the derived infinity category. If we just work with the triangulated category, then it doesn't have these kind of limits and colimits. But if we work with the infinity category, then we can make sense of a homotopy pulled back like this. And you can see the homotopy because if you want to glue something here, let's say alpha X, then as I said, you want to specify, you want to specify the restrictions, but you don't just want to say that the restrictions are isomorphic, but rather you want to specify the isomorphism as part of the data. So the precise statement is that there's some equivalence between this kind of data, this isomorphism. Sorry, this should be all on the restriction to the.
You said something about the structure from X restriction. You can have two different types of a restriction. Or the U and V are open. So
he said that the homotopy descent data do exist, and you have kind of bijection between this collection, which in the last line, on the right and on the left. It's kind of, without infinity categories, it's kind of intuitively pretty clear thing. In order to glue things, you should specify on each open subset, and on the intersection, you should specify an isomorphism. These are descent data.
Yeah, exactly. So this is just the usual kind of sheaf condition. But yeah, you can see that if you just take, I mean, this is kind of my Ravi torus property, because if we take this guy, there's an associated long exact sequence. But from the long exact sequence, you cannot really get a statement like this. you really need to, this is really some homotypical information here, which you need to remember. So that's why there's this infinity here or this homotopy here.
Mhm. So you and they are all assumed to be open, right?
Yeah, these are just open. I mean,
Okay.
there is more general statement with
For open
some,
set, there is no ambiguity on what type of a restriction it is.
yeah,
So
this is just a
upper star or
restriction
upper
to,
shrink. Mhm.
oh
Okay.
yeah, no, this is just yeah,
Upper
just a
star.
pullback. Yeah. Okay, so now this is kind of, yeah, classical, except okay, maybe this part is a little bit less classical, but yeah, now I want to talk about Voevodsky's formalism of motivic sheaves. So this is another kind of sheaf theory we can take. So in the algebraic context, if we define, okay, I won't tell you the definition, but we can, Voevodsky somehow define some kind of derived category of relative motives over X, with coefficients in some lambda. So for technical reasons, we have to assume either that the characteristic is 0, so either p equals 0, or you have to invert p. In positive characteristic, you just work with z adjoin 1 over p coefficients. Anyway, this is just because we don't have a resolution of singularities in positive characteristic so far.
Yeah, but lambda is what? Any commutative?
Yeah, just any commutative ring. Yeah. So the kind of universal example will just be this guy. So what is this kind of thing? I mean, over if X is spec K, this is kind of motives, just motives over K. So it's something which has a functor to to different functors to vector spaces. So there's a Tal realization to vector spaces, or there's a Betty realization, and with the X is a kind of relative version. So now there's realization to Tal sheaves or Betty sheaves. The definition of this is quite complicated using some intersection theory of what we now call Voevodsky correspondences. But anyway, so this is deep theorem, which in this form it's due to Sisinsky and Diglees that there's a six-functor formalism in this category. And there's also a rigid analytic analog of this due to Ayub. So what is the point of this from the perspective of this talk? At least, what is the point of this motivic machinery? It's just very simple. All I want to have is a kind of sheaf theoretic approach to Chow groups. So this is the Chow group of algebraic cycles up to rational equivalence, and then I work with lambda coefficients all the time. So this is just tensor with lambda. And this statement says that if I compute Borel-Moore homology in the motivic setting, so lambda mot is just lambda as a constant motivic sheaf in some sense. So this is a guy which lives in here. And so if I take this Borel-Moore homology in the appropriate degrees, I just get the Chow groups. And moreover, I mean, you can see this is only one kind of almost diagonal part of the grading. So this is a kind of Tate twist, by the way. But if we take some plus s here for any integer s, then we get these so-called higher Chow groups defined by Bloch. So we can refine this statement to a statement at the level of chain complexes, that the motivic Borel-Moore chain complex with the shift. So this is just a notation abbreviation for this. This is quasi-isomorphic to the Bloch cycle complex. So this is a highly non-trivial result, because this is really coming from complicated intersection theory of X, and this is a sheaf theoretic machine here.
So X is here what?
So here X should be algebraic, and in this statement, it should be kind of finite type scheme over K, over the base field.
Okay.
Yeah, maybe depending on your definition of Chow group, you should assume quasi-projective. Sometimes this is only defined for quasi-projective case. Okay, so now I want to talk about one more kind of generalization of this picture, which is a kind of introducing some stable homotopy theory. So instead of taking sheaves of vector spaces or lambda modules, we can take sheaves of spectra if we are working over a topological space. And then there is a recent result by Marco Volpe, which is kind of using work of, I mean, at least a lot of the work is done by Jacob Lurie, also in his book, Higher Topos Theory. So somehow, yeah, you can show that this category has the formalism of 6 functors as well. So we can also work with this kind of object. And this kind of lets us talk about generalized cohomology theories. So we can now, instead of taking a commutative ring, we can take a commutative ring spectrum in the sense of stable homotopy theory. And yeah, so for example, we can take a sphere spectrum, or we can take interesting cohomology theories like covariatism and K theory as well. And then there's of course, analog of this in the algebraic setting, which is Voevodsky's formalism of motivic homotopy theory, which, yeah, this he received Fields Medal for this proof of Bloch-Peto and Milner conjectures using this whole machinery of motivic homotopy theory. And then Ayub has defined some analogous setup again in the rigid analytic geometry over non-Archimedean base field. Okay, so yeah, the main result, which I want to just end this part with, is that you can extend these kind of things to stacks. So especially this DM and SH, so Vygotsky motives, and this sheaves of spectra or the motivic versions, they can be extended to Artin stacks. And I won't explain the proof of this here. Yeah, the talk is kind of different, but at least to give some idea of how this looks, we can compute the Borel-Moore homology of X, or the complex, as follows. So this is a limit, but it's really like a homotopy limit. So it's similar to the homotopy pullback we had before. In some sense, this is saying that, yeah, we can glue, if X is a scheme, we can glue this guy from these opens. And here it's kind of analogous, but the idea is that, okay, if X is a stack, there are not enough interesting opens, but rather we should look at the smooth side. So we should look at smooth morphisms into X. And so what we do is we take a homotopy limit over these Borel-Moore chains over all morphisms that are smooth, where T is just like a scheme or algebraic space. So it's kind of non-stacky. So we know how to define this guy. And then we just take this homotopy limit. And you can think of these transition.
Do they behave this Borel-Moore homology? Because you take smooth morphisms, not, I mean, not a tal or something like.
Yeah. So if X is just a Deligne-Mumford, then it's enough to take étal morphisms.
Yeah, but
yeah, for Artin, we really have to take smooth morphisms instead of only étal. And yeah, so I mean, you can think of these transition maps in this limit as a kind of Gizen map. So let's say the map from here to, I mean, let's say there's projection to any given thing, and this map is a kind of Gizen map along this this T, and so that's why there's a shift. This is kind of Gizen shift by the relative dimension, and we only have this kind of Gizen map in general for smooth morphism. So that's why you take just these kind of smooth morphisms in this limit. And yeah, but anyway, you see that it's kind of enough. So there are some consistency checks. So maybe this will help. Let's say if we just take a quotient stack where we have a action of a linear algebraic group on X, then we can compute these guys using the kind of like Borel construction, but yeah, in topology, the Borel construction is not, I mean, you leave the world of manifolds somehow, and similarly for schemes, you leave the world of schemes, but there's a approximation due to Totaro. So Totaro's approximation to the Borel construction, we can compute these things this way. So there's a kind of result underlying here that if we take this whole category of sheaves, the derived category of sheaves, if there's a fully faithful embedding, again, this is some homotopy limit of infinity categories. And these are some things which appear in this Borel, in this approximation. And these are some things where G is acting freely. So these are just schemes. And for example, BGM, you compute with PNs.
Yes,
So
so do you understand correctly that for these simple pieces, you take essentially like duals to equivariant cohomology of EU alpha at the level of cohomology, not at the level of complexes. At the level of cohomology, you take equivariant cohomology with compact support for this U alpha, which is dual to Borel-Moore, of course, and which can be computed just using the standard Borel construction. Yeah.
Yeah.
So
yeah, you could define it this way.
okay.
The way I compute it is more like an analogous statement. Just like for the Borel-Moore version, I just stay with Borel-Moore everywhere. So the statement is that this guy can be written as some homotopy limit over analogous things with the U alpha mod G's, and then there's some twist coming from the dimension of these U's.
So then for quotient stacks, it's essentially the cohomology reduces to equivariant cohomology, maybe.
Yeah, exactly. It's basically computing equivariant cohomology. So that's
just a second. So in this quotient stack case, is this category the same as Bernstein and the Nonce derived equivariance category?
I don't know. Yeah, I think it's kind of.
Or are they different?
I think it's a kind of infinity categorical version of this. I think it's slightly different as far as I know, because they could not really make sense of homotopy limit here. So they had to use some more complicated constructions from homological algebra to kind of get the right thing on this side. But I'm not too sure. I didn't study their construction in detail. I only looked at the cohomology groups here. So yeah, maybe there's some relation. I didn't try to find a precise statement there.
Yeah, that was in Bernstein and the Nonce in the one of the quite a long
paper. Right. Yeah, this is kind of the first paper on this kind of topic, right? But yeah, I didn't really try to compare directly with their construction. But yeah, I guess as Jan was saying, basically what we get is that in the quotient stack case, this is just computing equivariant. So in the motivic case, it's computing equivariant chalk groups. And rather, the complex is computing the equivariant cycle complex. So Edidin and Graham in their paper on equivariant intersection theory, they defined not only the equivariant Chow groups, but also an equivariant version of the block cycle complex. So when you take the cohomology of these guys, you get just the block cycle complex. Oh, there's a shift missing. Yeah. Then there's some work. I don't know exactly what the status. I mean, they haven't. So yeah, these guys told me they proved this result at some point, or at least they checked the details. I don't know if they are planning to write this. And then more recently, I was contacted by Kresh and Mantovani, who also claimed to check this result. In some sense, this result is just saying that Kresh also defines some version of Chow groups, and then this is just saying that for in this 2n part, so not the higher part, but just the ordinary part, we just get Kresh's Chow groups with this mild assumption of affine stabilizers. The idea of this is kind of obvious, because if you have affine stabilizers, then there's some result that you can stratify your stack by quotient stacks, and then in the global quotient stack case, it's just this isomorphism. And then you want to somehow say that in the localization long exact sequence, you can reduce to the closed part and the complement, but there's some subtlety about not having higher Chow groups on this side, because when you use the localization long exact sequence, you want to use higher Chow groups. So there's some workaround, because Kresh defines some first higher Chow group. Anyway, so there's some, morally this is kind of clear, but it turns out to be a quite complicated argument to check the details. Yeah, one other comparison I just wanted to mention, because recently Joyce wrote a paper on wall crossing type things, and he defined a new homology theory. And so I just want to point out that, instead of Borel-Moore homology, you can also define just homology by taking, again, the dualizing complex, but then taking compactly supported sections. So it corresponds to taking upper Schrief and lower Schrief of the constant sheaf. And so now if you take lambda equals Q and you work in the Betty setup and you take homology of this complex, that's what this side is, then there's a result which I will put on archive soon, hopefully, that this is the same as Joyce's homology for Artin stacks over the complex numbers. He also defined an equivariant version. So if you have G acting on X, now the point is X also can be a stack itself. So X is just some Artin stack. Then you define G equivariant homology with the 6 operations like this. And then Joyce also defined some equivariant homology. And in fact, they're almost, if you try to prove they're the same, you see that they're almost the same, but there's some kind of lim1 problem, because this thing, at some point there will be a homotopy limit here, and in Joyce's construction, there will be just a limit of the homology groups. And then there's a problem that we have some potential non-vanishing of lim1. So these guys will just be quotient of these guys, but these will have better properties in general. So that's why I say it's a kind of corrected version of his homology.
And what paper this about enumerative invariance?
The recent paper starts with enumerative invariance. Okay, so that's a part I wanted to say about the cohomological setup. And now I want to say some things about intersection theory in this setting. So I want to, my approach to intersection theory uses kind of derived geometry, which I will try to briefly convince you that it's helpful with this kind of question. So I will just introduce derived geometry very roughly as in just an analogy here. So a perfect complex, this is some, perfect complex is basically a kind of, if you don't know perfect complexes, just think of this as derived category of coherent sheaves or something, or at least derived category of vector bundles. And then a perfect complex, at least locally, is just a formal resolution of a coherent sheaf by a vector bundle. So somehow the idea is we have our not underived notion, just coherent sheaf, and we want to define a derived version of coherent sheaves in some sense. So we say, okay, the good objects, like the nice, projective objects, are vector bundles, at least locally. And then we just replace our objects in the category by complexes of vector bundles. So it's a kind of formal resolution by vector bundles. I think of derived stacks, and I think it's a good way of thinking of derived stacks as a nonlinear version of this, or like a geometric version of this somehow, where we start off with schemes. We want to define a kind of derived category of schemes in some sense. And we say that the nice objects are smooth schemes. And then you take resolutions of this. In this setting, you cannot just take a chain complex. Usually it's a little bit more complicated. You have to use some homotopy machinery like Quillen's non-abelian derived category and simplicial objects. But anyway, the intuition is the same. And so you have this picture. The top part is, the right column is a kind of linear and linear column, and the left hand is the nonlinear column. And we can go from a smooth scheme to a vector bundle by taking tangent bundle, for example. And then in the other direction, we can take the total space. And so we can kind of derive these functors to the tangent complex. This is like Quillen's or Eleusi's tangent complex, just the dual of the cotangent complex. And now you can also you can go in the other direction and you can take the total space of a perfect complex. I mean, this will, of course, this cannot exist as a scheme, but it does exist in the world of derived stacks. You can just take any complex and you can take like spec sim of this. So for
when
example,
you say total space, it's what? It's spectrum of the symmetric algebra.
Yeah, exactly. So if F is a coherent sheaf, then we can look at spec sim. And now here, if we have a perfect complex, we can take spec sim, except it's kind of, to be precise, it's a derived symmetric power. And this now exists as a derived stack, or this lives as a scheme. So this is not a scheme. Oops. This is not a scheme, but it's kind of only lives in this world of derived stacks. So for example, we can take the tangent complex, we can shift it, and we can call this the normal derived normal cone. So here F is any morphism of derived stacks. So for example, if F is a closed immersion between smooth schemes, then this complex is just, after shifting it, is just the normal bundle concentrated in degree 0. So in that case, this thing really is just a scheme, and it's just the normal bundle or the normal cone in the classical sense. But otherwise, it's some derived stacky thing. And then we have this theorem with David Ridd that there's a kind of derived functor, not just a derived functor of the normal cone, but a derived functor of deformation to the normal cone. So I call this deformation to the derived normal cone, which we denote by D, and this lives over A1. So this is some family over A1 where the special fiber is this guy, and all the other fibers are just constant, just kind of Y everywhere. And this is the same as the Verdier or Fulton-McPherson deformation if you just take closed immersion of smooth schemes. So once you have this deformation, you can do the classical construction of specialization to the normal cone, which is uses this localization triangle. So the closed part is the normal bundle sitting inside the deformation space, and then the open part, you restrict to the open part here, is just y times gm. It's a trivial guy here. Using the boundary map for this localization sequence, or yeah, similar to the classical construction in Fulton's book of specialization, you can just do a derived version of this. But the interesting thing here is this is just any map, not even closed immersion or anything, just any map. I am putting some implicit assumption that this thing is a perfect complex, but this is just some kind of finiteness condition, which I will implicitly put here. Okay, so this, what's the point of this construction? I guess, why is it interesting? So in the case when the morphism is so-called quasi-smooth, so this is a condition about where the relative tangent complex is concentrated, which geometrically it means the following thing. It's a kind of Kuranishi situation. So locally on X, you can factor your map like this, where M is a smooth morphism over Y. So M is some scheme which is maps smoothly to Y. And on M, there's a vector bundle, E, and a section. So this is the section. And this is the derived intersection of this section with the zero section. So this is kind of derived intersection here, but in some kind of derived sense, let me put R maybe for derived. Yeah, so this is the usual kind of Kuranishi setup where you, because this might not be transversely intersecting, so you have to, I mean, there's some discrepancy between the virtual dimension. So the virtual dimension would be the relative dimension of this guy, but then minus the rank of this vector bundle. That's what you would kind of naively expect the dimension of this over Y to be. But
Adeel, this relative tangent complex, can it have infinitely many negative?
Yeah, this will be, it will be bounded.
Okay, so
yeah, so if everything is kind of if everything is just a stack in the classical sense, like one stack, then it will live only in degrees 1, -1 to 1.
yeah.
And in general, if it's a kind of n stack, then there could be some terms in -n.
-n, okay.
Yeah.
Is that some kind of abstraction theory?
Yeah, exactly. So this, you can think of this as a an obstruction theory. I mean, so I think, yeah, a little bit later I will say something about perfect obstruction theories in the sense of Baron-Fontecchi, but in particular, whenever you have this condition, it means that if you look at the classical truncations of these derived things, you can pull back this complex to that classical truncation, and this will define a perfect obstruction theory in the sense of Baron and Fontecchi.
Yes, thank you. That was exactly what I was thinking.
Okay, sure. So this this specialization now is useful in this quasi-smooth setting because there's a theorem you can show that when you have this, this condition, and then you shift it, so now this normal bundle is concentrated in degrees less than or equal to 0. So in that kind of case, you have this generalized Thom isomorphism kind of statement. So basically, this is just the base, the Borel homology of the base with the shift, because this is a kind of Gizen map, like Gizen along the projection. So the virtual dimension appears here. So when you combine this isomorphism, you get some map from Y to X with a shift, which is a kind of virtual Gizen pullback. So this quasi-smooth is just a generalization of smooth. If we put 0 here, then it's the same as smooth. And in the smooth case, this is just the kind of classical Gizen pullback, but otherwise this is this kind of virtual Gizen pullback. So I should say this kind of construction appeared in a paper by Latyntsev with the title Virtual Gizen Pullbacks.
What is D? I forgot. It's just relative.
D is just the relative virtual dimension. And so in particular, if X is quasi-smooth just over a point, then we get a map from spec K, Borel-Moore homology of spec K to X. And if we just take the, the generator here, this will map to something here, which I defined to be the virtual fundamental class of X. And here, I mean, X is just any quasi-smooth Artin stack. And again, we can take any lambda here, so this can live in cobordism or motivic cohomology or any generalized cohomology theory. And also it's kind of agnostic to the geometry, so we could also do this in rigid analytic geometry or differential geometry and so on. But in algebraic geometry, there's, of course, the famous construction of virtual fundamental classes by Baron and Fantecchi. But it's kind of requires this Dewey-Milford-Ness hypothesis, which in particular means that you only have finite stabilizers. So this is the first, as far as I know, this is the first construction of a virtual class with infinite stabilizers. But in the case when it's Dewey-Milford, then it's the same. Under the, I mean, they constructed in the child group, but under this isomorphism with the child group and this Borel-Moore, these are the same. And yeah, as I said, this kind of construction we did here makes sense in any setting, so it's a little bit more robust. For example, in rigid analytic geometry, we don't really have any definition of child groups, but because of Ayub's construction of motivic cohomology of rigid analytic spaces, we can still make sense of the right-hand side. So this is useful. I mean, this is applied, for example, in recent work by Tony Yu and Mauro Porta on non-Archimedean version of Gromov theory.
Yeah, they cited you. Tony just gave a talk last week, so
yeah, we discussed a bit with Tony as well on this kind of thing, just to make sure that the constructions in my paper really work in the rigid analytic setting as well. Yeah, so one kind of non-stacky result I want to mention. I mean, it can be stacky, so this could be a scheme or a stack, but it's interesting even just when X is just maybe classical smooth variety, and you take some smooth subschemes. This is a kind of derived version of Bezout's theorem, which you can think of Bezout's theorem as saying that when the intersection is transverse, then the product in the child ring, cup product, can be computed by the intersection, the fundamental class of the intersection. So now it's just saying that even if it's not transverse, an arbitrary intersection, you can take derived fullback and you take the virtual fundamental class of that. So then this will always compute the right answer. This was a version of this was first announced by Lurie in the setting of Italian cohomology, but yeah, he never wrote this up. And then in my paper, I did this with this motivic machine in this setup. Yeah, so the last part, actually, I kind of took, I have exactly 1 hour, right? Is the usual time for the talk?
1 hour plus some small epsilon, yeah.
Okay. Yeah, so I'll try to be a bit briefer in this next part. So this next result is a joint with Diane Aranha, Alexei Latyntsev, Injun Park, and Charanya Ravi. So there's 2 main results I want to mention here. The first one is a kind of stacky version of Atiyah-Bott localization, which just says that if I give you a closed immersion of stacks, it can really be Artin stacks here. And you want to know when does a push forward induce an isomorphism up to localizing. So there's some subset here, sigma, some subset of cohomology classes, which I want to localize. And when will this be an isomorphism? And of course, this is kind of a classical topic, Atiyah-Bott style theorem. And the condition, so basically what we prove is just a general condition of this form. but the classical results would be really in the torus equivariant case. So X would be the quotient by a torus, and then you would know that, okay, I mean, then there's some condition like if this is the fixed locus, then this is always possible. But here, this is just a very general result that any closed immersion of derived stacks, as long as you could check some condition, then this will be true. So the condition is basically just saying that there are enough representations somehow in the equivariant case. But really, it's kind of about line bundles on this stack, that there should be enough line bundles because Euler classes are, yeah, basically you have to invert enough Euler classes of line bundles. So there's some condition.
What is the restriction L restricted? I even cannot read it.
So this is the this is the stabilizer or automorphism group at the point X, and this is the classifying stack of the stabilizer. So just when you restrict to this BG, where G is the stabilizer, then this should be trivial. But on X, on X itself, it should be non-trivial, and it should be in the elements that you invert. The Euler class should be there. So it's some condition which, yeah, when you apply this in examples, if you want to apply to quotient stack, for example, it amounts to showing that there's enough representations. So, for example, if you have a torus, then you can take sigma to just be the Euler class of the tautological bundle on BGM. So if T is like a higher rank split torus, then you pull back these Euler classes to T by the projections. And then the statement is that if here I look at the T stabilizer, so this is different from the stabilizer of the stack, and it's also different from the stabilizer of the quotient stack in general, because it's, X itself can have some non-trivial stabilizer. So I have to be careful about what exactly I mean here, but the T stabilizer is really just the stabilizer of the T action, doesn't see the stabilizers of X itself. Oh, this is supposed to be a curly X.
So stabilizer of the T action on what? On
the stack. On X, or well, I mean on the scheme. I mean in this case, so but the point is, even in this case, I allow X to be a stack. If X is just a scheme, then it's a little bit simpler. But yeah, this is the T stabilizer on this X.
Yeah,
so
but
it's just,
for example, like classical Atiyah-Bott, X is a kind of
so
scheme,
if X is just
even a smooth
scheme,
variety maybe. And so then the condition is almost, it's obvious,
yeah, exactly. This is really like for the stacky case, we have to put this condition that the stabilizers are kind of proper subtori, because we allow this. Oh yeah, I meant to say that X is allowed to be Artin stack. So yeah, we are working on like more. I mean, this paper is not written yet. Right now, we are trying to see how many more like equivariant localization theorems we can deduce this way. But in the K-theory version, we can get a slightly stronger statement, because we can replace existence of line bundles by just K-theory classes in this condition, and this lets us work with arbitrary reductive groups. So this is a kind of new result, as far as I know. Even if X is a scheme and G is just a like connected reductive group, this gives you some new version of localization in this sense. So I think, yeah, it's interesting. I mean, we still have to investigate further applications of this, but yeah, and of course, the other interesting thing here is that X itself does not need to be quotient stack at all. It could be some kind of moduli problem, which is not a global quotient. Like, for example, it can be moduli of coherent sheaves, or Higgs bundles on some smooth scheme. And so this will be some kind of Artin stack. And now you can try to reduce the Borel-Moore homology to some smaller locus with this kind of result. So there are some applications of this form, but yeah, I won't talk about them right now. I wanted to talk about the kind of second counterpart of this, which is, I forgot to put the assumption, but if X is quasi-smooth, then there's a virtual fundamental class. And we can compute the virtual fundamental class in this localized Borel-Moore homology in terms of the virtual fundamental class of the fixed locus, assuming that the fixed locus, at least assuming that it has finite stabilizers, because again, X is Artin, so there's some. Of course, the T stabilizers will be trivial, but we want the stabilizers of the stack itself to also be finite. And then we can prove that you can reduce this virtual class to this thing. So this is a kind of generalization of a Graber-Pontari-Pandey virtual localization theorem for the Baron-Fantecchi class. And even in that case, in the case where they work, where everything is Dilley-Mumford, they have some global resolution hypotheses on this vector bundle, on this complex, which we do not need here. And also, yeah, I should say I'm kind of hiding some things under the rug. What exactly I mean by the fixed locus when it's a stack. But yeah, it's not so obvious how to define fixed locus.
Is there any kind of intuitively clear example of this fixed point? Like, I don't know. I can kind of, let's see, for example, for, I don't know, for Higgs bundles, it's unfortunately not quasi-smooth because it has cohomology in degree 2. Yeah, I think.
Yeah. Yeah, I think the classical examples of this were for stable maps. Yeah, so maybe one example I can mention is if you have, if you look at like moduli stable maps to PN or something, and you look at the GM action on this guy. Mm-hmm. So this was used by Kontsevich in his paper on enumeration of rational curves.
But it's not an Artin stack.
This is not an Artin stack, but now you could try to do this computation when the base field is not a characteristic 0.
Okay.
And then you have some Artin stack, in positive characteristic, you have an Artin stack which has finite stabilizers, but it's not Dilley-Mumford because there's some ramification. And so it's a kind of simple example of Artin stack, but at least, I mean, even in that case, this is kind of new result that you can compute Gromov-Wittmann invariance in positive characteristic using this kind of formula. Yeah, that's the main example. And of course, this kind of thing is robust enough to also work in a non-Archimedean setup. So I hope that it would allow us to do some computations of non-Archimedean Gromov-Wittmann invariance. Even though in that case, everything is Dilley-Mumford, but still, even in the case of schemes or something, this was not really known for non-Archimedean case.
Can you say something about the T? Is it always a torus or just any reductive group?
For this part, it's a torus. Yeah, we are trying to see now how much this statement can be generalized to more general groups, but it's a bit tricky. But there's some idea using Daniel Halpern-Leistner's theory of what does he call it? He has an analog of, what we really use a lot here in this argument is the fact that we have a weight decomposition of the derived category of the classifying stack of the torus.
I see.
So we can decompose any perfect complex like this into 0 weight and non-zero weights. So Daniel Halpern-Leistner has some kind of analogous, analogous formalism for more general groups. So we're trying to see if this can be used to generalize it.
Okay, thank you.
Yeah, but we don't have any results yet. So the last part, not already close to the time limit, but the last part is kind of categorification of this story. So again, we have any morphism of derived Artin stacks. We can define a specialization functor of sheaves. So this will now take any sheaf in this category to monodromic sheaf. So MON stands for monodromic sheaves on the derived normal bundle. And you define this using deformation to the normal cone again. This has a canonical map to A1, and it's a GM equivariant map. And you use nearby cycles with respect to this. So this gives you a functor from sheaves on this guy to sheaves on the normal bundle. And this is just Verdier's definition when F is a closed immersion of smooth schemes, or LCI closed immersion more generally, in which case this is a classical vector bundle. And also it agrees, in the Betty context, it agrees with the Kashiwara and Shapira style specialization of submanifolds. Interesting thing about this categorified construction is that there is also a new thing you can do now, which is a Fourier transform. So the Fourier transform exchanges sheaves on vector space with sheaves on the dual. And so I claim that there's a derived version of this, which has the same kind of properties. And now you can apply this to this perfect complex, and this will go to the dual. And the dual of this perfect complex is it's just the -1 shifted relative cotangent bundle. So when you combine these constructions, you get a kind of microlocalization functor along the morphism, which again, this was studied by Kashiwara and Shapira in the Betty case, when you just have a closed immersion of smooth schemes over the complex numbers. It's the same, but yeah, but now you can do it for any morphism. So this is, this is just, it's a relatively new construction. So I'm still understanding, still understanding where it's going. But I just wanted to mention two things here. The first thing is that using this microlocalization, we can give another approach to the virtual fundamental class. So if X is now quasi-smooth, we have this sheaf, the microlocalized constant sheaf, which lives on the -1 shifted cotangent. We shifted for some reason to get the right numerology, but yeah, if we take the 0 section of this guy, there's a kind of Euler class. So somehow in the perspective of the 6 operations, there's a map from 0 upper shriek to 0 upper star, which if this was just a vector bundle, then this map would give you the Euler class of the vector bundle. But it's not a vector bundle, but still you can do this construction, and you can compute what everything is. You compute that this is just a shift of the constant sheaf. This is the dualizing complex. And so this map defines a Borel-Moore class, which is exactly the same place where the virtual class lives. And then the statement is that this is actually the same as the virtual fundamental class. So it's a kind of microlocal construction of the virtual class. So clearly the sheaf is encoding some interesting information, at least. Moreover, it's related to the recent categorifications of Donaldson-Thomas invariants defined by Joyce and his co-authors. So this part is, this statement is joined with Toski Kinjo, and also recently found out that PhD student of Ben Zvi and Sam Raskin has also independently considered this kind of construction, at least in some special case, and he proved a very similar statement. So yeah, the statement is that, again, if X is quasi-smooth, if we look at this microlocalized constant sheaf up to a shift to make it perverse, then this is isomorphic to Joyce's perverse sheaf, which categorifies the Donaldson-Thomas invariance of this guy. So this is some -1 shifted symplectic stack in the sense of Ponte-Vito and Vachier-Vitsosi, and there's some kind of generalized Donaldson-Thomas invariance of this thing. So as a corollary from this,
essentially a three-Calabi-Yau case, so it's not kind of a generalization. If you say that it's -1 symplectic, called the -1 symplectic, so it's kind of restricted to dimension 3.
Yeah. So this is really like Donaldson-Thomas theory of Calabi-Yau for threefolds.
Yeah.
But I mean, we don't really know how to define. I mean, we know how to. Now we know how to do fourfolds, but I don't know if there's any idea about fivefolds or a higher dimensional Donaldson-Thomas theory.
Yeah, there are some answers, but not theory. But in general, yeah, I mean, the idea kind of intuitively is very much clear. You take this Chern-Simons functional, it can be taken in any dimensions in the derived sense. So then the question is about foundations, how to define the sheaf of vanishing cycles. And
right.
If you are very persistent, probably you can do it in any dimension.
Right. Yeah, I mean, even for the numerical invariance, it's not really clear how you would define a virtual fundamental class in this case, right?
Yeah.
Yeah, but anyway, so this is just about the threefold case. So for example, if you take a local surface, meaning canonical bundle of a surface, then this is the moduli of sheaves on, this is the moduli of sheaves on. So yeah, basically, if we take X to be moduli of sheaves on the surface, then this will be moduli of sheaves on the local surface. And then this statement, it will tell us that you can compute the cohomological Donaldson-Thomas invariant of a local surface using microlocalization with respect to this surface. I mean, moduli of sheaves on the surface. And so in particular, because this thing is kind of motivic in the sense of Vygotsky motives, like we can use nearby cycles of Ayub to define this construction in the language of motives. And so this tells us, yeah, this is some kind of interesting observation, I guess. I don't really know what it means, but also there's some important statements about this guy called the dimensional reduction. And so from this perspective, the dimensional reduction is obvious. In fact, we already used it. Dimensional reduction is just this isomorphism here, because yeah, this is the same thing as projection of the constant sheaf as well. And dimensional reduction is just, sorry, not constant sheaf, I mean of mu. It's just that in the monodromic setting, the pullback of the zero section is the same as push forward of the projection. And so dimensional reduction is the analog of this statement, except where mu is replaced by this Joyce sheaf, this vanishing cycle sheaf. Yeah, the last part I just want to mention is in progress that we have some micro-local construction. We still need to compare it with the Borisov-Joyce invariant. So this is the fourfold case. So for Calabi-Yau fourfold, we get a -2 shifted symplectic space, and Borisov-Joyce defined a virtual fundamental class for this guy. And using this micro-local setup, we have another candidate for this construction, which we believe is isomorphic to I mean, equal to the force object class. Yeah, so that was the last slide, so I'll stop here.
Yes, thank you very much. Are those stacks quasi-smooth for Calabi?
For Calabi,
yeah,
they're not quasi-smooth because they will have, in general, -2 shifted will have things in degree 2 and so on. So, yeah, you cannot really use the classical virtual fundamental class in this case.
Yeah. Okay. So, are there any questions? By the way, about this relation to the enumerative geometry, so you somehow, in the more or less unified way, can define this virtual classes, so you have whatever invariants you have, even if they kind of exist in the derived sense only. But there are some strange results which I think they do not have scientific explanations, like the relation between Gromov-Witten and Donaldson-Thomas invariants for threefolds. They don't come from the comparison of the virtual classes. Yeah, so then I'm just curious, is there any I don't know, derived reason?
Yeah, that would be interesting. I mean, if there's some relation already on between the moduli spaces, but yeah, it seems quite, at least the statement in the form that it's proven seems to be like very far from this, I guess. So
it doesn't look that the spaces kind of, but maybe, I don't know, in the derived sense, like physicists would say that very naively, instead of stable maps, you consider their coherent sheaves supported on the, of rank 1 probably, supported on their images, on the images, whatever that means. And basically this is probably, this gives a map in some higher sense between stacks. But the problem is that there, in order to compare to generating functions, you kind of take one of them, which is in the powers of one small parameter, but then you recalculate it. You have to prove that something is rational and expand it in a different point. And this, I don't see how to make sense unless there is some analyticity result or something like that. Okay.
Yeah, I see.
And kind of another question. So I'm sorry, maybe I'm stupid, but the moduli, you mentioned the stack of Higgs bundles. Can this localization be applicable? Is it quasi-smooth?
The Higgs bundles, I mean, there's two forms of localization. I don't know if this has any application to Higgs bundles, but yeah, this says something about Higgs bundles. In this statement, there is no quasi-smoothness. It's only in this statement because the statement is about virtual fundamental class. But
yeah, but may I ask you a philosophical question? So this is general, yeah, exactly. But kind of in practice, it is known that abelian localization theorem, it's kind of it appears in the much wider class of examples, but non-abelian is kind of very difficult and sometimes wrong. So what's the reason for that? I mean, if you...
It's, I mean, from this perspective,
It's
it's just,
philosophical question, but some conditions which you require, it's easier to check.
yeah, from this perspective, you can see in this statement that if you take a torus, then you can just see that there's enough, enough line bundles that, I mean, there's just this tautological bundle on BGM is kind of enough for this statement.
Yeah, but for that, for the abelian, you really need quasi smoothness. I think, yeah.
Oh, yeah. What do you mean? You mean for this statement?
Yeah.
Is your question why is?
No. The thing is that I have. I mean, it's a practical question. We have some kind of running project with Roma Fedorov and my son Alex, which kind of computes sort of Donaldson-Thomas invariants for moduli stacks of Higgs sort of for two-dimensional Calabi-Yau categories, like moduli stack of Higgs bundles with some additional maybe like parabolic structure, blah blah blah. And so it would be nice to reduce the computer just to define the invariants as kind of, in a sense, as integration or some virtual class, maybe in some higher sense, and then to reduce the computation to some localizate to the fixed locus of the action of the torus. Yeah.
I see.
But
yeah, but I think you should. I mean, in your setup, you work with these motivic invariants, right? Rather than the virtual fundamental class.
Yeah, but I would be glad. I would be glad to have it in the way. What's I mean, just because.
Yeah. So I think that this kind of statement could be lifted to this Borel-Moore thing. I mean, the virtual fundamental class is kind of different. I mean, I don't think. Yeah, one should think of this as analogous to the class in the growth and decreasing of varieties. But this thing is more analogous to the class in the growth and decreasing of varieties. And so
if I localize with respect to, if I have a torus section, then you have kind of, I forgot it's on one or the next slide. Yeah.
You mean
this one.
Yeah.
Yeah. Then yeah, is it kind of simplifies the computations? It's clearly it's easier to check this property, but in terms of the computations, you should kind of be able to compute this Borel-Moore homology of the fixed locus of the fixed.
So I guess
said that it's complicated thing for stacks. This substack of fixed points, it's kind of complicated. Do you know where?
Yeah, but one can kind of bypass this difficulty a little bit, because I mean, in this statement, we don't need to know what the fixed locus is for general torus action on a stack. If we just have like X is some moduli space and we have some simpler subspace, we can just try to check this condition directly for that case. So for example, I mean, what I saw in the literature, this kind of statement being applied to the Higgs bundles was like X is moduli of Higgs bundles and Z is just the moduli subspace where the endomorphism is nilpotent, this kind of subspace.
Nilpotent form, yeah.
Exactly. And so at least in some case, they were using this kind of computation. Yeah, they were using this kind of reduction from X to this guy, and then computing something here. which my impression was also in your paper, it was similar, right? You somehow compute the motivic class of the nilpotent cone explicitly.
Yeah, but in some, but it's sort of, yeah, it's similar in the spirit, but you see there are many technical details which, at least for us, they make it impossible to combine all these details in a short, nice quasi-isomorphism as you wrote. Yeah, so it's quite also, as far as I know, all these computations were done only for the group GLN, so for GLN Higgs bundles, and you see your kind of your theorem is so general that it does not kind of, I mean, it's just starting stack and that's it. The only thing is that probably for torus localization that it's not quasi smooth, probably, yeah. Okay.
Yeah, but somehow, I mean, this reduces the problem of computing this to the problem of computing this, but then you still have to do some computation here. So maybe there's still some, yeah, I don't know how, I'm not too familiar with computations of these things yet, but
yeah, but basically
I'm not sure how
it's like what you say, that kind of, if you have just, if you replace, say for GLN at least, if you replace the Higgs bundle by sort of a pair consisting of a vector bundle and endomorphism, yeah, Higgs bundle is not a Higgs field is not an endomorphism; it's a map from vector bundle to vector bundle twisted by a canonical class. Yeah, but for endomorphisms, indeed, you can reduce it to the nilpotent endomorphisms, sort of analog of the nilpotent cone. And then if you have a nilpotent endomorphism, say of vector space, you can replace it by vector space with filtration, yeah, like by kernel of the powers of your nilpotent endomorphism, same for vector bundle. And then basically this object, at least if you go to the associated gradient, it's fixed points of some torus action, of some sister action. Like filtered objects, yeah, you know, like associated graded, it's direct sum, so you have torus, you have characters. So morally, it's kind of the same field, but technically, it's much more complicated. I would be glad to have just one shot, kind of this kind of result, which reduces immediately to the computation of some much simpler object.
I see.
Yeah, maybe. But you said that this set of fixed points, it's a complicated thing.
Yeah, but I think this is, I mean, the definition of this is sort of like if you just want to, yeah, I mean, the problem is,
for example, for the quotient stack, let me ask you a stupid question. If X is a quotient stack by some smooth, say, scheme modulo some group G, all right? And what's this XT?
Yeah, well, I mean, so basically there are two things which I can say. So first of all, I mean, this is not the case which will interest you, but just to say that, I mean, if X is Dilley-Mumford or Artin with finite stabilizers, then it's known how to give a general definition of this thing. This is, even in the Dilley-Mumford case, it's kind of highly non-trivial. It's a recent paper of Alper, Hall, and Rid in Annals. I mean, as an application of their general machinery. But even in that case, it's not just a kind of naive definition. You have to somehow take into account reparameterizations of the torus and so on to, yeah. So, but yeah, in general, if X really has infinite stabilizers, then basically we don't, I mean, yeah, we have some construction of what this should be, but we do not really know yet that it's algebraic, that it's like art and stack. Instead, what we proved, the actual statement of this result in general is a little bit different. It's the statement is if you just take a closed, so you forget about this xt, you say, okay, I don't know what xt means. You just forget about that. And you say, you prove a statement that if you have a T equivariant closed immersion where the torus action is trivial on this part, and it's also quasi-smooth and so on, then you have a statement of this form. So you just forget about this this question, and but then it's hopefully useful in
actually, it's a good idea indeed. You need just a closed immersion in your kind of main theorem, and then you can take Z, what sort of you guessed is a stack of fixed points. Okay.
Exactly.
Yeah, good idea. Yeah. Okay. All right.
Yeah.
Good. More questions?
Actually, I was going to ask about the Vygotsky sheaf or the ring spectra, but time seems to be strained. In the future, I might read first, and then I'll send you email, ask questions.
Okay. Yeah, sure.
Thank you.
I'll be happy to.
Very inspiring talk.
Actually, the idea was, I mean, originally I asked Adeel to give a lecture series, but unfortunately this Miami conference, it's killed kind of the week. We could not, it's supposed to be the previous kind of the Miami conference week, but maybe we will ask you after all, maybe in the next academic year to give that course. Yeah, because
I'll be happy to.
details are interesting. Yeah.
Yeah, thanks very much for the interest. Yeah, definitely. I mean, I tried to cram probably too much into this talk, but yeah, I hope there was still some.
It's good. It's kind of a bigger picture. It's a general. Actually, maybe I ask you to send me again your slides, but with your corrections, because you corrected several.
Yeah, I will make some corrections and send you the updated one. Thank you.
All right. So, are there any questions? Last chance. Well, if not, thank you very much. Really interesting talk, and looking forward for that paper which you promised.